driving forces why we need to rapidly decarbonize and then remove carbon dioxide out of our atmosphere. And then talk about why enhanced rock weathering is a particularly great fit for that, to address the climate crisis, and then also some of the co-benefits that comes with using a nature-based solution. So, yeah, as Chris already wonderfully introduced, I used to work in the world of particle physics, spent over a decade, starting with my PhD at UCL, working on SuperNEMO, and then working on the Lux-Zeppelin experiments, and all of those rare event search experiments led me to work mostly in some of the deepest underground facilities, such as nature, since we're constantly hiding from cosmic rays. So I spent a lot of my time at the Bowlby Underground Laboratory, and then also the Sanford Underground Research Facility in South Dakota. But yeah, my first area of research for sure, it's not on gambling, but on neutrinous double beta decay. And working on the SuperNEMO detector at UCL. And then that was followed up by my postdoc and subsequent fellowship here at the University of Edinburgh, working, from my PhD, I also worked on the Lux detector upgrade, and then upgrading to LZ, and then subsequently at the start of some conversations to build the next generation of dark matter detectors. And that's in large part kind of where my journey in that area kind of came to a halt. And if people are interested in the reasons why, largely it was because the nature of these long experiments meant that the G3 dark matter detector were likely going to take 7 to 10 years R&D to construct, and then data taking for longer. And there was an opportunity that arose to move into the sector for decarbonization, which was the one area that was very important to me outside of particle physics. I still deeply love particle physics, but this was probably the one area kind of largely due to the existential crisis nature of that in the ever narrowing window, decided to make a move. But if people are interested in that journey, I recently shared that in a blog post, so I'm happy to share that with the organizers, and then they can send that around in case people want to read about it. But the main reason, so in repeated IPCC reports, and there being 4. The first report came out in 2021, and it really highlighted that climate change is this widespread and rapid and intensifying event, and is unequivocally as a result of human-induced greenhouse gas emissions. So I think that was the first ever time scientists unequivocally linked climate change to human activities, and that was quite a major news headline. And then that was subsequently followed by the second report in 2022, which, the headline news, all life on Earth, not surprisingly, from ecosystems to human civilizations, is vulnerable to a rapidly changing climate. And then the third report in the latter half of 2022 kind of stated that the deployment of carbon removals to counterbalance the hard-to-abate residual emissions is unavoidable in order for our path to achieve net zero. So this report kind of really outlined the need to rapidly decarbonize, as always, but still accelerate technologies that can allow us to actively remove CO2 that have already been emitted into the atmosphere in order to truly reach these net zero goals. And then finally, the last report, which in 2023 stated that there's a rapidly closing window of opportunity to do all of those things in order to secure a livable and sustainable future for all. So I guess these are the scientific motivations. And then the numbers that fall out from these various reports are that, essentially, at the minimum, there is a need to remove some order of 10 billion tons of CO2 per year by the year 2050. So currently we emit something between 46 to 50, about 50 billion tons of CO2 a year, and increasing. And so in order to reach the net zero goals on various projections, and I'll talk about how these break down, we would need something remove about 10 to 17 billion tons per year by 2050. And then critically, yeah, reducing emissions still the most powerful impact we can have, but it alone isn't enough, and we need to also undo some of the damage we have already done. Then that's where undo comes in, as this name suggests. We aim to maximize the amount of carbon dioxide we take out of the atmosphere in order to create a positive environment for the future. And the technology we aim to do that with is something called enhanced rock weathering. But before any enhancement, just going to talk a little bit about rock weathering. Rock weathering is a natural process that's happening all around us all the time. This process is part of Earth's long carbon cycle and is part of Earth's natural carbon regulation system. So it begins really with rain falling through the air. As that rain falls, the CO2 in the atmosphere dissolves into the rain to form very mild carbonic acids. And when those acids fall onto mineral-rich rocks, such as basalt, they react with those rocks, breaking the rock down, and then forming bicarbonates and cations instead. And then those bicarbonates and cations are washed out by the rain into river systems and ultimately out to the ocean, where it's locked away or stable for geological time. So that's 10 to 100,000 plus years. So this is kind of broadly the equation of governing that entire process. And that whole process takes many, many decades from CO2 out of the rain to finally reaching the ocean. And I guess the question we're asking is, how can we utilize and accelerate this natural process in order to draw down carbon dioxide faster? And there's really like a couple of ways you can do this. You could choose very fast reacting rocks. So there's lots of silicate rocks that will weather, break down very rapidly and draw down CO2. And for example, those materials are like basalt, wollastonite, olivine. They each have advantages and disadvantages. For example, olivine was probably the first weathering silicate or first rock identified to be optimum for rock weathering. But due to its fast weather, but it has this unfortunate link that the faster the weathering, the olivine, the naturally more potentially toxic elements it contains. And those are kind of like chromium and nickel. That's in the olivine. So then there are also wollastonite, for example, which are very, very fast weathering still, but very, very clean in terms of very low in potentially toxic elements. But in both cases, there are not huge stockpiles of it in the world, and undo is primarily focused on deploying basalt, which is another fast weathering silicate, very low in potentially toxic elements, but it's very readily available. So to give an idea of scale, instead of something that weathers in 2 or 3 to 5 years, basalt, the same kind of basalt probably weathers over the course of 20 years. But in the scheme of deployment wise, there is far more basalt readily available. It's globally covers some 5+% of the Earth's surface, and almost all volcanic output rocks are basalt. So, and there is already a large industry that quarries basalt. So that all of these make it very attractive material to work with for large scale deployment on the gigaton scale. So, and then the next big thing to do to accelerate this whole thing, and that's where the word enhance comes in from enhanced rock weathering. The enhancement is just powderizing the material. So, you can imagine a lump of rock will take 1 million years to fully weather. But if you can powderize it, increase the reactive surface area by 6 orders of magnitude, that same lump of rock now weathers in 20 years instead. And I think the analogy I always give is like kind of if you're trying to make coffee in the morning and you just chuck beans into a French press, you're going to get a very disappointing brew after hours of waiting. But if you crush your beans, open up those reactive surface areas. So if you're coffee beans, you can get a very potent coffee very quickly. And so kind of a similar idea in this case. And the overall process kind of looks like this. So you have your rock. I'm not sure this is from our branding team, but I'm not sure the Giant Causeway is the best. We're not actively going to destroy the Giant's Causeway, but it is a great demonstration of what basaltic rock looks like. And they are, very pretty. So you take your rock, you powderize it, and I always describe enhanced rock weathering as three-win scenario because you don't actually have to do any of the crushing right now. There is a multi-gigaton scale industry already that exists to quarry and crush basalt. And they use that for roads and buildings. So the aggregate industry already mines this material. And when they crush it, the fraction that they actually leave behind that they don't have any use for is the sub 4 millimeter basalt because it's too fine to be used in roads and buildings. So right now they're just left in these huge stockpiles. So here, this is like a 10-meter stockpile, which our CEO is standing on top of pending health and safety risks or whatever. But just to demonstrate that, these giant deposits of these are byproducts from the quarrying industry. And currently we estimate some 600 plus million tons of this byproduct is created annually that have no use and are just kind of left behind in the landscape or disposed of in landfills. So so that's the first win, is that you don't have to do any crushing. It's already there for you. So you take this byproduct. And the second win is that you don't need to build any roads, infrastructures, or machinery to spread it. You can use the same roads, and this is the standard farming equipment. This is a liming equipment, and you can just spread your rock with the standard farming equipment that's already there. And then once it's spread, it will still start breaking down, start weathering, start drawing CO2 from the atmosphere. And as it does so, it also has various chemical processes that improves the soil, increasing the soil pH, the soil structure, and then also yield on occasions has been demonstrated to be a boost by enhanced weathering, which I'll talk more about later as well. So that's good for the soil, good for the farmers. And then the third biggest win, of course, it's great for the climate because it's drawing down CO2. And then ultimately, all of this ends up in the ocean many years down the line, where you could argue that, so when it reaches the ocean, it will precipitate to form calcium carbonates. And that has the fourth added bonus of reversing some of the effects of ocean acidification, but that's a bonus win years down the line. And the whole process, from our estimates, is, so we've done this over many hundreds of thousands of tons at this point, but the process, so we limit ourselves to spreading only within a 20-mile radius of the quarry that we operate out of to minimize our own carbon footprint. But we've done a LCA life cycle analysis when we were spreading within a 50-mile radius of quarries, and that whole process was more than 95% efficient, which means that the carbon footprint that goes in to get this material on the ground is less than 5% of the total carbon dioxide it's expected to remove. And now we're operating within the 20-mile radius. It's a lot better than that still. Yeah, so, and all of that is just to fit in with Ondu's vision, which is to keep the planet fit for future generations. And the mission is to be the first company to remove 1 billion tons of CO2 per year and help deliver that sustainable impact solution for climate change. And right now, as Ondu is a company of 70 plus people operating both in the UK, in Canada, Australia, and also Kenya and Tanzania. And also recently we had operations in the US. And everything we've built is designed to scale. So we have a very replicable design in terms of how we scale to new areas, new continents, new countries, in order to reach that 1 billion ton removal. And all of that is designed to fit in with the Paris Climate Agreement. I think the 1.5 Celsius goal, regardless whether or not it's currently on this trajectory of being feasible to achieve, is still something we should do everything we can to aim towards. But in order to do so, it requires rapid decarbonization, as I mentioned, but also new technologies to come in order to maximally draw down carbon dioxide from the atmosphere. And the current pledges are not enough. We need to do more. Because if we don't, the results are 2-degree warming, global crop failure. We're already seeing that in many countries now. We had a drought in Scotland for 4 months last summer, and they were shipping water to some islands in Scotland, which is something no one's ever heard of before. So, I mean, obviously it's a single event, but it's happening definitely more frequently. and then 4 degrees mass human extinction, and at 6 degrees, Earth uninhabitable for life, which is, doesn't sound great. So it'd be nice to avoid. To say the least, and the best way to do that, in order to meet the climate agreement goals, is rapid decarbonization, so rapidly reducing our emissions. By far, the easiest thing and the cheapest way to reduce to get to net zero is to reduce the amount of CO2 we emit, whether it's switching your power and heating to new renewable sources, more efficient buildings, improving public transport. There are lots of ways to decarbonize, but I'm not going to focus at all today. But this is obviously the most critical. But I'm actually going to focus on the other 20%, which also is very critical, because there will reach a point when there are industries which are hard to decarbonize any further. And in order to continue the kind of society we're currently living in, albeit a very decarbonized version, the IPCC still expects some 20% residual emissions, which has to be removed from the atmosphere in order to reach those net zero goals. And to date, there are broadly, I think I try to summarize all the existing carbon dioxide removal technologies. And one of the reasons why it's really key to scale all these technologies really is because the total sum effort of human carbon dioxide removal to date is about 200,000 tons. That is globally everywhere over the last decade. And where we need to get to is 10 billion tons per year. So, everybody in the room is probably well aware of how many order of magnitude we are off where we need to be. And that's why we need to invest and drive these technologies now in order to get there. So I think I try to summarize the technologies and highlight why enhanced rock weathering is a powerful technology to get us to the gigaton removal. So, the first thing I kind of try to highlight is permanence. So I think over the last few years, there's definitely been a move away from low permanence solutions for carbon dioxide removal into high permanence. And what that means is that if you plant a forest, it will draw down carbon dioxide very fast and at a very cheap rate. So that's afforestation. And it has co-benefits. All nature-based solutions have some nice benefits for the environment, assuming you're planting biodiverse forests and you're doing everything right. But even then, the tree will die and it will decompose and it will re-release some 90% of its CO2 back in the atmosphere, unless you have a system to deal with that. For example, you can combine it with biochar. Biochar is where you can heat your biomass at a very high temperature, oxygen-free, to create biochar, which then locks your carbon away for 10,000 years. But it's not a high permanent solution, and it's quite expensive. And then so each of these have challenges and benefits. But I think where enhanced rock weathering stands out is that it is high permanence. It can be deployed very quickly because we already have the rock, we have the roads, we have the farmland. Doesn't compete for land. It can deliver very cheap carbon dioxide removal and has the co-benefits. So it sounds all too good to be true. So where's the catch there? I think the biggest catch for enhanced rock weathering is accurately quantifying how much carbon dioxide you're removing, because the rock's being spread over such a large area. And that whole process is under this umbrella term called MRV, which stands for Measurement, Reporting, Verification. And the remaining of this talk will be kind of around how Undo aims to do that and how different sciences can really contribute to accelerate this kind of technology. So so we take a measure model approach, which means that right now we are deploying lots of field measurements to accurately measure how much carbon is being sequestered, whilst all the while developing a geochemical model in order to model that out to multi-decade scale. And then we want to move to a future where we can combine and use those two in combination. So I'm going to kind of slightly reverse those and talk about our model first. So the model we are developing is based on one that's being extensively peer-reviewed and published. It's a one-dimensional reactive transfer model that was developed at the University of Sheffield as part of this Leverhulme Center for Climate Mitigation. And that was developed over many years at Sheffield. And part of that team, so Peter Wade, Amy Lewis, Mike Kellen, who are part of that development team, have now since moved to join the Undo model team, and we're continuing to make improvements on the existing model that's kind of out, that's openly available in public. But the model is still useful because even though we don't use it to quantify carbon sequestration, it's good to use the model to give us projections of what we might expect from our deployment. So, for example, we have an internal cutoff when we come to selecting rock. So we don't want to ultimately be spreading rock that's not capturing carbon dioxide. So we actively choose the best rock, and I'll talk more about that in just a minute. And then we have an average ratio of 4:1 in terms of carbon sequestration of our material that we deploy, which means for every 4 tons of rock we put down on the ground, we expect after 20 years it would sequester 1 ton of CO2. Yeah, so and then the model gives us that ability, and the model kind of take into hundreds of different input parameters, but largely they're across 4 different key categories. So the rock itself, so the mineralogy of the rock, the dissolution rates, the reactive surface area, application density of the rock, climate, so what part of the world you're spreading in, the temperature, precipitation rates, and then soil parameter, where you're spreading on, the soil pH texture, and all the soil input parameters, and then atmospheric parameters. So all of those feed into the geochemical model. And as I said, the reason that is important is because we know from our own study, so for every single quarry we're operating out of right now, we take rock samples in advance to do XRD, XRF, ICP-MS measurements to make sure that the rock has good mineralogy that will sequester CO2. And we've seen out of the 400 plus quarries that we've analyzed that the carbon dioxide removal potential of the rock can differ by as much as 6.5. So we have an internal cutoff which says that we need at least a 5:1 ratio for rock to carbon sequestration potential before we would use a material. And we recheck that rock for every 3,000 tons we remove from the quarries just to make sure that the mineralogy remains consistent. But also very critically, since we're working with agricultural land that produce food for human consumption, our number 1 priority is always don't contaminate the land. So we check the basalt for potentially toxic elements like chromium and nickel as well. But naturally, it's very low occurring, but still, there are no guidelines around such parameters in the UK and other places. So we found the most stringent guidelines for soil amendments, which are EU guidelines that we hold ourselves to. So in terms of what we can then put on the ground. And then we also test every sample for reactive surface area because we've seen that have differed and that can affect your carbon dioxide rate by up to factor of 3. So in all things, we try to understand our feedstock as well as possible. And we built some fun tools behind the scenes, as you can see on the right, to pull global data sets that's available so that in this case, we can tag a single quarry that we have identified and then tag all the agricultural land within a 20-mile radius of that quarry and then run model runs across each of those points and have a kind of a weathering heat map of what the weathering potential using that quarry can be with the feedstock from that quarry. So yeah, and all of those information then go into the model. So this is one standard quarry we have here near Edinburgh. You can see that the rock from there mainly composes of 5 different rock phases: augite, andesite, smectite, quartz, glass. As you might expect, glass doesn't weather much at all over time, but andesite weathers very quickly. And then so as each of these weather away, they release bicarbonates and cations, and we apply a charge balance calculation to work out ultimately how much CO2 can be sequestered. And then we sum all of these up into a single carbon sequestration or carbon removal curve over time. We do all of our modeling out to 50 years, but you can see for this quarry, 20 tons per hectare applied on the field. At 20 years, we expect just over 4 tons of CO2 to be removed. So that's actually right around about the 5:1 ratio. We also have quarries that are much higher than that, but as I say, the average is 4:1. But this is essentially how all the carbon removal calculations are being done behind the scenes. But that's kind of just for our own internal projection. In terms of actually, generating carbon credits, we take field measurements, which I'll come to next. But once you have all this data, you can kind of play around. This is just tagging all UK land where there are more than 15%. So these are in 11 kilometers square blocks. So each dot represents 11 square kilometers. And the reason for that is it's actually 0.1 degrees. So in each of these points, any point which have more than 15% being agricultural land is identified. And then we can look at all those input parameters that went into the soil. So, the temperatures, pH, cation exchange capacity, rainfall levels. As you can expect, it rains a lot more on the West Coast than the East Coast. And then take all of those variables into effect and then run a large modeling out to the 20 years to see how uniformly does it weather in the UK. And actually, you can see it weathers broadly, very uniformly across area. And actually, the UK fall under technically a same weathering region, even though people who have lived in the UK might argue otherwise. And that's because even though it rains more on the West Coast, it's actually much warmer on the East Coast. So, and lots of these parameters balance out to ensure that you have pretty uniform weathering. So this map just kind of stretching the axis out. You can see that even at the 50-year mark, you only have a very small, narrow margin of variation between where weather's the most and where weather's the least. And then if you accumulate all of those variables in, you can generate these Monte Carlo histograms to show like the projected out where the weathering could take you over the next 50 years. And then you can do some fun analysis where projecting each month slice onto the y-axis to build a histogram of cumulative carbon dioxide removal for that month using, and then you can then kind of, which then allows for the mean and standard deviation to be calculated for each month. And then using that, we can kind of do some analysis and work out that we have maximum uncertainty at the 16 years, a month mark. And even at that point, though, it's only about plus minus 4.5%. So, and that kind of makes sense. So you have maximum uncertainty, and then as you're fast weathering rocks like Andesine is fully weathered, your uncertainty is significantly reduced over time as well. So that completely tracks. So that's from our modeling side, and then I will just talk a bit more about the measurement world. So as the rock breaks down, there are various proxy signatures you can measure. There is no single probe that could directly go into soil and measure bicarbonate and cations, and that would be really the dream, but unfortunately it doesn't exist. So we try to use as many different techniques to measure those weathering proxies, and that includes changes to soil pH, changes to crop yield, changes to the rock itself, and then also the bicarbonate and cations released from the rock breaking down. And that broadly looks like this, right? So the world of this is being in academic research for the past decade, and they've come up with various different techniques to measure proxies to show that weathering has taken place. But this is UNDO is the first time that we're trying to do this on a large scale in the field, not in a laboratory condition. And our vision to do measurement is to try to combine all of these techniques to build as a holistic picture as possible of weathering so that we can very accurately quantify how much carbon is being sequestered. So that means that we put the rock down and we measure the rock for its physical breakdown, which I'll talk more about later. And then we track for the proxy, so the bicarbonate and cations in the water that's moving through the soil column. So we take pool water every 2 weeks to track that at multiple different depths. And then we're tracking for the movement of those weathering products moving through the soil into nearby river systems. So we're then aiming to track river chemistry changes, and then ultimately that migration from rivers to ocean. We're trying to track how long that journey takes. We're also then digesting the plant to track the uptake of cations by the plant, because there are also nutrients for crop, which is why you have yield improvements. And then by adding all of those together, we can track as accurately as possible how much rock is broken down and how much product is released and how much of that is going to get into the oceans, where it will be stored permanently for that geological time. And right now we have trials. So we have 50 trials in the UK. So they include small plot trials and split field trials. So small plots are kind of 4 by 10 meter plots with 3 different application densities, 6 replicates, and then split field is kind of just 1 to 5 hectare field split in half basalt amended, half not. And we have trials in the UK, US, Australia, Canada, wherever we operate. We try to deploy a diverse range of field trials to cover the major crop types, the major soil types, and the major climate zones in order to track the different things that might impact weathering. And yeah, and all of those measurements, as I said, then feed into our model as well. So we use those measurements to physically calculate carbon dioxide removal in order to generate carbon dioxide removal credits. But then all those data are really invaluable as well to test the geochemistry model we have and continue to track how well that model is working in terms of comparing the model outputs to our field data. And all of this is ideally, we want to build a model which, after 5-7 years of data testing, then can work robustly across different climate zones, different soil types, different crops, and be able to kind of model to a degree of accuracy that then only requires a smaller number of measurements in order to cross-check and confirm instead of the current kind of measurement densities. But yeah, but one of the key areas I think just since we're in the particle physics world has been really revolutionary in collaboration is that one approach to measure the dissolution of rock has been really taken off. So that's kind of here in the measurement techniques, physical rock measurement. This was a technique pioneered at Yale. It was published last year called TICAT. So what that means that you can directly measure the weathering of your rock by tracking the immobile elements within it. So let's say your basalt has lots of calcium and lots of titanium, and soil has a much depleted of both. By measuring your soil sample that also contain rock, you can work out how much rock is there because you understand your feedstock well, you understand your soil well. So by mixing together, you know how much calcium to titanium you expect to increase. And then as that rock breaks down, the calcium is leaving the system, but the titanium remains in the soil. So by taking repeated measurements, you can track for the ratio of calcium to titanium over time changing, and thereby demonstrating that your rock is breaking down. So that's kind of shown on the bottom right here. And this is the approach that, as I say, Yale developed and published last year. But the accuracy you need for these measurements are beyond most commercial ISO accredited labs do not even handle HF for rock digest, let alone enable you to do reduce your analytical errors to sub 1%, which is what you need in order to see this very minute change. So we are sitting at 20% application. So you can see the change from 25% of rock weathering is very small. And if your analytical uncertainty is anything more than 1%, it's basically impossible to resolve. But, the world of particle physics has, thanks to our incessant need to build ever cleaner detectors in both neutrino and dark matter, has a facility. So in the UK, it was at UCL and now also at Bowlby. We have these triple quad ICP-MS for measurement of uranium and thorium down to parts per trillion sensitivity, but they are also ideally suited. The expertise and equipment are there ideally suited to also make these TICAT measurements in order to support carbon, in order to support the throughput needed for quantifying carbon sequestration in the enhanced rock weathering world. So this is just one area where particle physics really overlaps with particle physics really overlaps and can really kind of revolutionize how we measure rock dissolution in enhanced rock weathering. And then another one is we have a PhD project at UCL right now trying to use neutron activation in order to tag the bicarbonate and track their movement through soil. So there are new innovations and where definitely new ideas could improve this technique. Yeah, so that's kind of from the measurement front, what we do to measure carbon sequestration. And all of those data then we feed to an external independent body, and then they they then allow us to generate carbon credits as a result. But I'm just going to finally finish off by talking about the co-benefits of enhanced weathering, because it is a nature solution. This is not new. If you think about how many civilizations have risen and fallen near active volcanoes because it has very fertile, rich soil, it's a similar process. So it has lots of benefits to the environment that you spread it in. So we've been able to demonstrate that rock weathering can kind of, the chemical reaction of rock weathering increases soil pH, making the nutrient that's already there more readily available to the plants. It also releases macro and micronutrients. So this is the table of that rock we saw earlier, what the nutrient content of that rock is in terms of as a fertilizer. And then also boosts soil microbial activity and improves soil structure. And it has been demonstrated and suggested to stabilize soil organic carbon, although that's an area that's out for more research. We run trials with Newcastle universities, and we saw a similar response in that front, where after 1 year application on spring oats, this is at the Nafton farm, which is a Newcastle research facility farm. They saw on average 15% yield response increase in spring oats, and critically, they also saw the expected pH increase across the different cultivation techniques, and then also critically no additionality of potentially toxic elements in the crop. So this was great news. We've just put all this together. Our publication has been accepted and is due to come out in mid-March. So look out for that. If there's any interest, I'm happy to share that around. But yeah, so those are the co-benefits, and then the impact ultimately. What is how impactful can this be? And we estimate just from the current feedstock in the UK, it can contribute to some 45% of the removal requirements for UK to meet its net zero emission targets. And then globally, there's huge availability of land, agricultural land. So this is ideally suited for China, India, Europe, US. And areas, and also Brazil, because it's a tropical zone, lots of rainfall, that's very warm. But these areas could benefit immensely from enhanced rock weathering. And then just to say, yeah, there's also a lot of rock around, and what a 1 million ton carbon dioxide removal looks like is essentially a circle with a radius of 25 kilometers. So I live in Scotland, so I've just taken the Loch Lomond National Park. This area deployment of basalt is essentially what a megaton looks like, which would be 5 times all collective human effort to date. But to get to scale to gigaton scale, there have been nature publications to optimize the deployment of rock on fields and suggest that enhanced rock weathering can contribute to some 4 to 5 gigatons of annual removal when applied correctly. So that's the kind of impact that this technology can have. And then, yeah, just last thing, I want to shout out to the great science team that's Undo. I think it's a privilege to work with a very interdisciplinary team. So, I'm a particle physicist. So that's why Chris's introduction is correct. I very much lead and build the team. I don't do as much science as I probably would like. But we have microbiologists, we have geochemists, isotope chemists, we have just kind of analytical chemists. We have ocean people who've studied ocean alkalinity for decades. And then also, Christina, our research lead, spent a decade in Greenland monitoring greenhouse gas emissions. And, and I think enhanced rock weathering has been this geochemistry problem for like a decade. And I think by bringing these different points of view, it can really accelerate and drive the technology forward, and then get us to a net zero future sooner. So I think, yeah, definitely. For example, one thing that came out last year was somebody demonstrated that enhanced rock weathering can reduce greenhouse gas emissions, mainly nitrous oxide. Just so happens our research lead spent a decade doing that in Greenland. So we were able to very quickly deploy trials to test that and demonstrate that, yes, by more efficient use of nitrogen fertilizers, you can indeed reduce nitrous oxide emissions. So yeah, so lots of very cool expertise within the team, and where we lack expertise, we also are very open to academic collaborations. I think to date we have some, we have 20 plus academic collaborations with various universities and national labs, from developing sensors to developing protocols. And then we're also very keen to work with industry partners, so analytics and Agilent, to develop new techniques to better digest and measure the rock and soil. Yeah, so if there's any interest in the room for new ideas to collaborate on, we're very keen on that. And we last year we have 4 PhDs starting with UCL, Newcastle, Glasgow, and James Cook University in Australia. So we're also very open to academic partnership in that way. So please do reach out, and happy to take any questions. Thank you very much for listening.
Okay, let's thank XinRan for the excellent talk.